Similar to talking about motion before, after talking about Newton's second law, we started talking about the concept of work and energy. Work still means a transfer of energy either into a system or out of a system. If you remember before, we said the work was some sort of force acting over some sort of displacement. So the object had that force exerted on it while the object moved. In terms of rotational motion, we can talk about work. Work is the torque. So again, a torque is required to cause rotation. So torque times the angle that the object moved through. So it still is some sort of torque over a distance, but a distance is measured in radians. It turns out we can talk about energy in general as well. When we talk about kinetic energy being 1/2 mv squared, this is called translational kinetic energy. I'm going to put a subscript of T on it. It accounts for the motion of an object as it is moving from one place towards another. Rotational kinetic energy is for any type of rotational motion around a rotational axis. The equation for that is 1/2 I omega squared. So I being the moment of inertia, omega being the angular speed. Now, an object that is rolling along a surface has both types of kinetic energy. It has translational kinetic energy because, let me get an object. So if it's rolling, it keeps rolling across the surface. It has translational kinetic energy simply because it's traveling from one place towards another. So that's translational. I might have just said rotational, sorry. So translational kinetic energy simply because the object as a whole is moving from one location to another, but it has rotational kinetic energy as well because it is rotating around a rotational axis. So anything rolling along a surface has both translational kinetic energy and rotational kinetic energy. If an object is rotating about a fixed axis, it has only rotational kinetic energy. So for example, if I was holding a meter stick right at the end and I released it, I know it would rotate downwards towards the bottom. And so it would only have rotational kinetic energy in that motion because the rotation axis is not moving. So in terms of energy and kinetic energy specifically, an object rotating about a fixed axis, a rotation axis that's not moving, the axis itself not moving, then the object will only have the rotational kinetic energy. If the object is rolling along a surface, then it has both. Now, in terms of gravitational potential energy, our equation for gravitational potential energy is mgy. Well, why? Let's go back to this meter stick. If I'm holding the meter stick horizontal, I release it from rest, I know the force of gravity, we can treat it as if it were acting only at the center of mass. That's the point of the center of mass, is to simplify where we can talk about the force of gravity acting. So I know this meter stick is going to rotate downwards. It will speed up at the very bottom. It will have some sort of rotation rate, omega, angular speed, and it will continue rotating back up some sort of distance based on how much friction there is between our fingers at the end. But ultimately, we could talk about conservation of energy in this aspect and say that all of the gravitational potential energy the meter stick has initially has turned into rotational kinetic energy at the bottom. This all rotational kinetic energy down here. And so if we say mgy is equal to 1/2 I omega squared, we need to know what to put in for y. It's a meter stick. What part of the meter stick do I look at? Well, since we're talking about gravity, we need to talk about where we're showing gravity as if it were acting. So since we describe gravity acting at the center of mass, this y needs to be the location of the center of mass. So if we want to use our lowest point as y equals 0, we need that to be the lowest point where the center of mass is its lowest point. And so initially is where the center of mass would be located originally. So if this is a meter stick, as I mentioned, the center of mass is in its center. We would say y initial was 50 centimeters, or half the length of the meter stick. So we just need to look at how high the center of mass is at any given moment. So initially, it's exactly half the length of the meter stick high. I comes from the table. Now, the meter stick, as far as the table is concerned, we could model it as a thin rod rotating around its end. So off the table, I would be 1/3 ml squared. So again, make sure you're looking at that table in the test notes as well as in the textbook so that you know what the different objects are and where the rotation axes are. Here, if we were to solve for omega, see the 1/2 cancels and L cancels. That leaves us with G on the left side. So 3G over L will be omega squared. But then we can square root that. So the rate, the rotation rate or angular speed of the meter stick at its lowest point would be .4 radians per second. And the whole meter stick would have that speed. But this is an angular speed, and that's why every point on the meter stick would be rotating at the same rate. So energy, we can use conservation of energy anytime we want to relate some sort of height to a speed. If you remember, energy did not include time, unless we talked about power specifically. If we were just using conservation of energy, then we were relating a spring or some sort of height that the object would move through. such that we could relate it to some sort of speed or height at the end. So let me scroll here for just a second. So conservation of energy, our equation is still the same. And this is the same equation we had written in chapter 10. We can still use this for rotational motion. Gravitational potential energy, as I just mentioned, is still mgy, but the y needs to be looking at specifically where the center of mass is located. A spring, if we happen to have one, would still be 1/2 ks squared. So the big difference here is gravitational, we have to remember to look at the height of the center of mass. The other difference here is that we now have two types of kinetic energy. Translational kinetic energy, 1/2 mv squared. Technically, this is v of the center of mass. It's the speed at which the object is rolling at in terms of meters per second. Rotational, 1/2 I omega squared, because the object is rotating around an axis. Work external would still be due to some sort of push or pull that is not gravity or a spring, and not static friction. Static, or I guess our author refers to it as a rolling friction, is what allows the object to have rotational kinetic energy. So we're accounting for that in terms of the rotational kinetic energy. Delta E thermal is only due to our kinetic friction. I'm not going to ask you a question that has both rolling and sliding. So the object would need to be sliding to have this delta E thermal. We're not going to throw that into the mix. If our object's rolling, it's going to be rolling without sliding or slipping. And so we actually won't need to worry about a delta E thermal. Well, I guess I should say, technically, okay, I need to take that back. Because this could technically be our torque multiplied by our angle. If you watch the video about the axe pushed against the grinding wheel, and it caused friction that made the grinding wheel slow down. We solved this problem using Newton's second law. Technically, if we knew the torque and the angle moved through, we could account for that in terms of thermal energy. So that's why I need to take that back. I'm not going to ask you a question about an object rolling along a surface and sliding, but you could potentially look at the thermal energy in an example of like the axe pushed against the grinding wheel. So conservation of energy will work for anything like the meter stick we just talked about, release from rest, how fast is it going at the bottom. It will work if we talk about an object rolling up or down a hill. So if I have some sort of object and I release it from rest, it's going to roll down the hill, and we can look at the speed of the center of mass at the bottom or the rotation rate of the object at the bottom. And vice versa, rolling up the hill would work as well. The omega and v are related by the radius of the object. So if you remember the relationship between translational motion and angular motion, we can use that relationship to plug in and relate v and omega together in our equations. So the next couple videos, I will do a couple examples so you can see how we use this. And I'll go through a few conceptual questions as well.